here, Young's modulus, matrix Young's modulus, fiber volume fraction, and matrix volume fraction. And this is the overall Young's modulus of the panel in one direction. Okay. Now I want to talk about why it has this form in next few slides. But you can see it's not a normal rule mixture. The normal rule mixture just have volume fraction. This one has Young's modulus mixed in. So you can see that if the volume fraction is high and that phase that material has higher impact on the overall property, right? But this material, this property kick in. So for thermal expansion, the rule mixture is a little different. Now, can you imagine if you have a whole bunch of material glued together, they try to auto-expand different amount, what happens? Now, we know the fact that these materials expand different amounts, right? You know, epoxy expands a whole lot more than fibers. Epoxy expands 63 ppm. Then the fiber expands much less. The fiber actually shrink a little bit in fiber direction, right? Now, at the material level, what do you think they will do if you put a bundle of carbon fiber in epoxy? What will happen? Let's say you marry them together in your curing temperature. Let's say is whatever 400 F, and that's a stress-free state. And then you start to have them cured and then bring them down. What happens? And the material want to shrink, right? Cool them down. And the matrix want to shrink a lot more than the fiber, right? Now they have to strike a compromise. Just like you and your little brother, sometimes you fight, so you have to strike a compromise, which is in between. So the material overall shrink to a certain level. That level is not the amount fiber want to shrink, it's not the amount a matrix want to shrink, it's in between. They fight, they compromise. Okay. All right, so we'll look at the derivation. So if you imagine that the fiber runs in the horizontal direction in the single lamina, the matrix also fill in the space between fibers. Due to the fact that they have different thermal convention, there will be stress between them. I guess one material wanted to expand, the other one material want to shrink. They will actually, one material will see compression, the other will see tension. But overall, there's no external loads. So the material, you know, the different phases of fighting, there are no external loads. If you cut the material in half, is there any stress in the cross section? What would be the stress? If you imagine you cut a material in half, what would be the stress in the cross section? None? Or there will be some? It's correct. It's none in every sense. But in the microscopic sense, there's some. Because there are certain phases are pulling, certain phases are compression. Or on average, it's none, but at the local level, there is. Right? Just imagine that you put two different metal together, copper versus whatever. You bond them together, you put heat on it. There's no external load, but the thing will bend actually, because they're actually fighting each other. One want to extend more than the other. Okay. What if how to design something that actually is two material that doesn't bend? You make it symmetric. You make a copper, aluminum, copper, symmetric. But if there's stress in there, there's still stress in there. The fact that they shrink, they fight, they didn't bend because it's symmetric. In a fiber reinforced composite, you can imagine it's composite, but there's still fights. What this equation tells you, there's no overall load. The first equation says this, on average, there's no load. But there is actually internal stresses, fiber and matrix, because they're different tendencies, they're different desires, they fight. But they must balance each other. So the stress in the fiber and stress in the matrix must add up to zero. So one could be tension, the other could be compression, and vice versa. Okay. All right. So you can calculate basically the stress in the fiber and the matrix is the total strain in the fiber minus the thermal expansion strain. This alpha F is this property here. If the carbon fiber is here, if the glass fiber is here, this is basically carbon fiber thermal expansion. Okay. This is a strain in the fiber. And this is a strain in the matrix. This is what matrix want to expand. Okay. The difference is the mechanical stress. This is the overall strain minus the thermal expansion strain. The remaining is the mechanical strain. Strain due to mechanical stress. Okay. This is just the equation. This is the same equation you learn in solids. If you read the chapter that talk about thermal effect, talk about this equation. So we basically use the same equation. This is basically solid mechanics model. So you can actually estimate what is the fiber stress, what's the matrix stress. You stick this stress into this equation here. Basically, this requires that whatever stress they generate due to infights, you have to balance. It's an equilibrium condition. The other way to say, we're enforcing an equilibrium. And you just plug them in. You can solve what the fibers, what the stress is, what the strain, what the overall strain it is, that give you the balance. And you call this, you can do a little bit of a simplification, and you call this factor the overall composite thermal expansion in one direction. One is the fiber direction. Okay, and so this is basically, and this whole thing under here is the equivalent Young's modulus in the fiber in the one direction. So that's actually E1. So this actually give you 1 over E1, these properties. Okay. So E1 is this group. That's rule mixture for E1. This is E1. Okay. Okay. That basically is how this how we come to this conclusion. The alpha 1 equal to this. Okay. So if I ask you to estimate, give you all these constituent properties and volume fraction, I'll ask you to how to estimate the thermal expansion for this lamina in the one direction. You just pick the whatever property and stick into this equation, and you get your results. And it should be pretty close. The one direction, the thermal expansion should be estimated pretty closely. It's similar to E1. Okay. All right. Now, E2, alpha 2 is the thermal expansion coefficient in the transverse direction, which is a lot more complicated. And the reason is that you have less of a constraining effect, you know. So basically, how to say that? So they also have fights, but you know, usually if you have fiber, a matrix bond together in this direction, they have more constraining factor in the fiber direction. But if when they grow in the transverse direction, they have less constraining effect. You have some freedom to grow. You have more freedom to grow. Just like like you have a row of people, different heights, Yao Ming versus me. If we had to glue together, we had to, in the same height, we had to fight. But if we just grow fatter, it doesn't matter. We just can expand it this way, it doesn't matter. So same thing when you have, in the two direction, in the transverse direction, the fiber can grow fatter, a matrix can grow fatter, the whole thing can grow a little bit fatter. But there is some constraining effect. But when the fiber matrix grow in the transverse direction, there is Poisson effect. They also constrain. So so basically, when the fiber and matrix are bonded together, we look at the transverse direction expansion. This condition is enforced. We're basically saying you can grow whatever you want in the transverse direction, but you had to guarantee in the one direction you bond it together. You don't grow different height. Your fiber matrix and in the one direction has to maintain the same heights. Okay, that's the condition enforced. And then you can estimate that. What is the so that will result in stress. That will result in a stress in the fiber matrix direction, even though you're looking at the transverse direction expansion. Okay, so this condition will translate to this. So there will be some stress due to the strain in the one direction. So if the fiber direction strain is this number, you can calculate the fiber direction stress. Use Hooke's law. This is Hooke's law. Okay. Again, that equals to this. So this E1 is this number, and we require that the fiber and matrix maintain the same strain, whatever that strain is. They have to match. Okay. And then due to this strain, there will be some stress in the fiber. There will be some stress in the matrix. Okay. They all equal to this number in one direction. Okay. And in a two direction, they just add up. In two direction, the fiber here, matrix here, the two direction strain, it just, they just build up, whatever, So this is the build up equation. The two direction strain is the build up of fiber strain and matrix strain in two directions added together. Okay. I mean, of course, this scale by volume fraction. If you have a more matrix, this thing will have more contribution to it. If you have more fiber, this thing will have more contribution to it. Okay. Now remember to use when you calculate the strain in two directions, you got to use the thermal expansion in the transverse direction to account for this. Okay, so we basically can further write this out. So this term expands to this. Okay, and this term expands to this. This is basically this term is contributed by two things, two physical terms. One is its natural tendency to expand in two directions. The other one is due to the Poisson effect, because the fiber has stress in one direction. If the fiber has stress in one direction, it'll have strain in two directions due to Poisson effect, right? This is a Poisson ratio. Now, if you pull a fiber, the fiber is gonna shrink a little bit, push it a little, expand a little bit. So that's the Poisson effect. This is just its natural tendency to grow in the two directions. So this two together is this term right here, which expanded this term. Okay. Same story here. This term is these two terms together. It's a natural tendency to grow plus a mechanical effect, Poisson effect. And you put them all together, you plug in chug, and that gives you the E2. And you take delta T out. Delta T, you pull delta T out, and you can equate whatever left over at alpha 2. That will be the effective thermal expansion coefficient for the two direction. It has many more terms. Fiber Poisson ratio, volume fraction, and this term is actually happen to be the Reuleaux-Mixture equation for new one too. So you can simplify that a little bit. So that equal to this. All right. So that basically is the derivation for this this part. This is the equation for predicting thermal expansion in the transverse direction of lamina. Okay. This is all the thing that go into it. Fiber properties, volume fraction, matrix property, volume fraction, and also this factor goes in here. So you have to calculate this first. This alpha 1 goes in here. That actually is a factor contributing to alpha 2. Okay. Any questions? All right. There's some example here you can read through when you do problems. It's just basic numerical. it shows you how you calculate based on these inputs. Fiber property, matrix property, fiber thermal convention, and volume fraction. It's essentially just plug and check. This is provided so you can check your understanding and do some exercises. Pretty straightforward. I will not waste time on this, but anyway, I'll just point out this is the last piece of, and there is a homework. That's your homework number 3. It basically is exercise designed to for you to go through all the equations in the slides. You can find solution in all these slides. You read through this, you find the right equation, plug number in. Should be easier than the other 2 homework. But this is the third one. You can once you finish homework 2 was due the end of this week, right? And this is due the end next week. Okay. All right, so that's everything about micromechanics. And I want to start to work on the main thing we're going to cover in this subject, in this text, in this course. It's the classical laminate theory. So we're building up to this. So basically, this is the one that we're going to do some programming about. This is the most widely used theory in designing of laminated composite plates. It's the standard for most of the design calculations, okay? And that's the most basic ones. There are much more advanced theories, but they all build up from this basic series, okay? So what it's designed to do is allow you to analyze a composite plate. Plate means that it has a 2-dimension. It's a three-dimensional object. 2 of the dimensions are much bigger than the third one. That's called plate. Okay, this is a plate. The thickness is much smaller than this 2 dimension. That's plate. If this dimension is much longer, and then the width is also small, we call it a beam. A beam has 1 dominant dimension. A plate has 2 dominant dimensions. If every dimension is big enough, then it's a 3D object. You got to do some other method. If this plate is straight, we call it plate. It's flat. If it's curved, we call it shell. And a lot of people call plate and shell theory. When they say something is a shell theory, that means curved. Okay. So we're dealing with flat ones. Now, shell theory and plate theory are very similar. If you understand plate theory, it doesn't take much more to understand shell theory. Okay. So we assume each lamina are the layer. For composite plate, we assume it's made of many layers. You can see the little layer drawing here. Each layer is a quasi-homogeneous isotropic material. It's basically similar to a prepreg cured into a layer. It's very thin. It's in a state of plane strain. And then all displacement are small compared to the thickness. And Kirchhoff hypothesis holds. The Kirchhoff hypothesis means that if you imagine there's a perpendicular line to the plate, and then you bend the plate, that perpendicular line remains perpendicular to the plate. You guys remember the theory for the beam? When you learn the basic beam theory, MI over I, what is the underlying assumption that go into the derivation of those things? Yeah, there's something called neutral axis, right? And their cross section. There's assumption actually. The fundamental, the basic beam theory has an assumption that the cross section perpendicular to the neutral axis remain planar after deformation. It doesn't warp. That's the fundamental assumption that go into the beam theory. That basically results everything you learn after. Okay. Now for plate theory, it's more complicated. For beam theory, there's only one way you bend it. You have a perpendicular line. This is a neutral axis. they remain perpendicular, they remain plane. That's the two assumptions. Now in plate theory, you imagine the whole plane, everywhere you can draw, there's a midplane somewhere, everywhere you can draw a perpendicular line to it, right? And you can imagine that when the plate bends, this perpendicular line also, everywhere it moves a little bit, right? But at the location where that intersect this midplane, that perpendicular condition remains. All right, let me draw a picture. So if this is a midplane, none of them work. Nice. Okay. All right, so if this is a plate, if this is a midplane, let me turn on the camera so these guys can see. Let's see, how do I turn the camera on? Yeah. Good. I hope you can see. I turn the camera on. So this is the perpendicular line to the midplane. Remember, imagine this is stretched out this way. The perpendicular lines. All right. Now you bend the plane. I'll draw some overlap. Let's say you bend this.
Yes, I'm trying to get some information about a car that I put on hold.
The midplane bend to this here, and this line remains perpendicular to it everywhere. This line goes with the deformed shape, but this line remains perpendicular. The material point at this point translates this point. So all the material point on this line is moved to this line. All the material point on this line moved to this line here. All the material point over here moved here. All the material point over here moved here. This is a Kirchhoff assumption. This is basically the most important geometric assumption. I'm drawing bending this way. Actually, it doesn't matter which way you bend. A Kirchhoff assumption, you can bend it this way or twist in 3D fashion. The Kirchhoff assumption says this normal, this line, A prime A, remains perpendicular to the plate, okay? As you can see later, you can get all this strain condition calculated from this assumption. Okay, so when we're dealing with classical Lyman theory, we're dealing with small deformation. We're dealing with a plate that deform a little bit, not a whole lot. If it's a plate deformed like a piece of rubber that wrap around itself, that's actually too much. This theory cannot handle that. The classical Lyman theory only can handle very small amount of deformation, okay? All right. So let's introduce some nomenclature. The plate, since it's made of multiple layers, we have to have a way to communicate the structure so that there's less confusion. So typically you put a coordinate together. You describe. You use you can use XY to describe in plane, the midplane. You find a geometric center of the plane, the top plane, bottom plane, the center plane. You call it XY.
CK-MAN.
And you have a Z direction. Z direction is perpendicular to the plane. All right. Let's do it this way. And then we can have many layers. We can design the layer furthest away in the negative end of Z. We call layer 1. And then you just going further down. You call layer 2, layer 3, layer 5. Each layer has a thickness. So you can basically come with two numbers, Z sub I and Z sub I plus 1. that define a layer. So for example, layer 1, in terms of Z location, is between Z0 and Z1.
Sure.
That's the spatial location of the layer 1. Layer 2 will be between Z1 and Z2. I mean, it's just a convention. You can define them.
095.
Define the the physical domain of each layers. Okay. And then each layer, there is a fiber orientation. Remember, we typically designate fiber direction in that layer as direction 1, and the perpendicular direction as direction 2. That's a material coordinate. We call them material coordinates. And that material coordinate may not be the same as the global coordinates. Your global coordinates x and y in plane, and your fiber direction, each layer could be off. So we designate the angle for it. So if I tell you all the layer, if I tell you the thickness of the whole plate is h, and then Z0 obviously equal to minus h over 2, right? And then Z1 is some number less than this, right? And Z2, if I give you a table that gives you all the Z's, you would know the thickness of every layer.
That's where it was located, and then I'm calling today to try and get it transferred.
And then I tell you for each layer what the theta is. That will be the fiber orientation for that layer. If theta equals 0, that means the fiber runs in the x direction. If theta equals to 90, that means fiber runs in y direction. If theta equals to 45, that means fiber runs in this direction, right? Fiber, if theta equals to minus 45, it means fiber runs in this direction. This is a positive, and there's negative this direction. Is that clear? And then you can write basically a bracketed code to designate this laminate. This laminate you can see has 5 layers. This is a partial information. We don't have the thickness. We also need to know how thick each layer is. But this bracketed notation tell you the orientation of the fibers. So we have a 0 degree. Obviously, you need to designate which direction is your x. You need to know which is x. Everything measured with respect. See the theta is usually that's understood without.
Yes, I have a car.
There's some understanding where the x is.
Newport News, Virginia
let's just put that way. Once you know what the x is, then you can basically designate it fiber direction of each layer based on x. In this one, top layer, let's call this top, this bottom. Top layer, basically fiber runs the same direction as x. We call it 0. Minus 45, 90. So this layer is perpendicular to x, right? 90.
It's Addison Blackman?
60 is 30. Okay. This is a 5-layer. Some people call this a fiber architecture for the laminate. It basically designated fiber orientation for each lamina. Okay.
Okay, thank you.
All right. A little variation. Basically, there are different kinds of shorthands. This kind of shorthand is meaning that there are 2 layers of 90. Sub 2 means there are 2 layers of 90. This one actually has 6 layers. Top layer, bottom layer has fiber running in the x direction. And 45, minus 45, 60, and then 2 layers of 90 in the middle, right? You see this code as well. This means symmetric. This means that this plane here is a symmetric plane. So you have plus minus 45, 0, and then 0 minus plus 45. Plus minus 45, 0, that's this. Plus minus 0. And then symmetric means 0 minus 45 plus 45. See, if you draw an axis over this direction, top and bottom symmetric. You see the symmetry?
All right, thank you
now,
so much.
if you swap this, it's not symmetric anymore. If you do plus minus, it's not symmetric anymore. It becomes anti-symmetric.
I'm doing well. How are you?
If it's symmetric, this minus, this must be minus. This plus, this must be plus. Same angle.
Yes.
Okay. So this shorthand. So when you have a sub S, that means this is a symmetric. So the total number of layer is actually 6. Plus minus 2 and then 0 and then minus multiply 2. Total 6 layer. Is that clear? You can see if you separate them out, the 2 zeros in the center, there's 2 layers here. Minus 45, minus 45, no. Plus 45, plus 45. This later has implication on the symmetry of ABD matrix. Once you build a stiffened matrix of plates, whether it's symmetric, anti-symmetric, or it'll affect the 0 terms on ABD matrix. We'll learn that later. All right. So this is another code. That means it's symmetric, but this is only a single layer. You put a top bar on there that designate that layer in the center. It Correct. Doesn't get duplicated. Okay. So these two are symmetric, and this layer is single. Okay. You could have different material, so you can have a superscript designate the nature of that layer. This means the 0 layer here is graphite. Plus minus 5 the boron, B boron fiber, or G glass fiber, whatever you. So plus minus 45 is boron, and then symmetric. So you have 2-type material, a total of 6 layers, 4 layer of boron epoxy, 2 layer of graphite epoxy. Okay.
That's kind of the car that I've always wanted. So I didn't actually know you guys had one in stock.
So there's some typical terms, descriptors for laminate. When you speak of balanced laminate, what does it mean? When you speak of symmetric laminate and cross-ply laminate, quasi-isotropic laminate, what does it mean? Let's go over them one by one. Symmetric laminate is pretty simple. It's just what we said. So for every ply above the laminate midplane, there is identical ply an equal distance below the midplane. So if you imagine the midplane of the plate, the midplane is this plane. This is a very important plane. Almost as important as the neutral axis in the beam theory. The midplane. So for symmetric plate, if there's layer here with certain orientation, there's at the equal distance on the other side, there's same layer. Always symmetric. Okay, that's symmetric plate. This is a balanced laminate. For every plus theta orientation, there is another minus theta, but it doesn't matter where it's located. So this is a loose requirement. Let's say you have plus minus 45 next to each other above midplane, that balance out. But for every plus theta, there's minus theta. It doesn't require where you put it. And you can have a plate which is let's say 6 layer laminate plus minus 45, plus minus 30, plus minus 10. It's not symmetric, right? You have 6 in that sequence, plus 45 minus 45, plus 30 minus 30, plus 10 minus 10. If you do a midplane, it's clearly not symmetric, but it's balanced because it falls into the second category. For every plus theta, there's a minus theta, right? Now, if you change your sequence, you do plus minus 30, plus minus 45, plus minus 10, it's still balanced. Plus minus 30, plus minus 10, minus 45. You split 45 on top and bottom, it's still balanced. So this is a loose requirement. This is required that where there's plus theta, there's minus theta. It doesn't matter where you place them. As long as there is balanced. Okay. Cross-ply are the laminate basically consists of mostly 0 or 90s. There are no other orientations. So it's all 0, either 0 or 90. That's called cross-ply. This is a quasi-isotropic ply. It's interesting. Yes. So this is actually so quasi-isotropic laminate is the one that if you don't know its orientation, you cannot see where the fiber runs. You cannot see. You cannot. You don't know the orientation. You cut a strip in any orientation, and you pull it in your tensile machines. They behave like the same. So you can use these composite lamina to build a structure that behave like that. It's called quasi-isotropic. There are no preference in any orientation. If you do 0-90, there obviously will be orientation which is strong, which is 0-90, and 45 will be weaker. But you can build a fiber orientation. You need at least 3 layers. And it behave like isotropy in all directions. We can prove this later on with our ABD matrix. I can tell you the way to put them is you make the orientation 120 degree apart, like triangle. You build this repeat units. It'll be isotropic, quasi-isotropic.
It's October 11th, 1996.
It's used quite common in situation when you want to have plate which is appear to be behave almost like quasi-isotropic. Obviously lighter and stronger in all directions. Okay, it's a very special layup. Any questions? Is that clear? All right, now I come to the theory. I may have just gave out the answer to the question 1 in your homework. So anyway, if you're smart enough, this answer is right here. So we're now looking into the consequences of Kirchhoff function. So we basically imagine a very small deformation of a portion of the plate. We look at the cross section, a sectional plate with many layers. We imagine there is a normal line. This normal line after deformation moved to here.
Yes.
So this line pivot a little bit. It has 2 angles. One's the pivot with respect to x, the other pivot with respect to y. So this is basically this is a look at x direction. That's y direction. X, y in plane direction. So if this is x, that's y, and z is this direction. So this angle, this line rotated. If I'm the vertical line, it rotates this way in the xz direction. Also rotate this way a little bit in the xz direction. That's what it. This is 2 cuts basically. This is xz cut. This is a yz cut. So this basically show you how much this is sort of normal has rotated. Okay. All right. And also this point has moved a little bit. This point has moved a little bit. So you can have a displacement function that describes how this point moves. U function.
It says that there's a lean on the vehicle.
U function describes how every point moves from the original configuration to the new configuration, right? If you know the coordinates, you pick a material point x, y, z. You plug it in here. This tells you how much this point moved in the x, y, and z direction. That's what we call the displacement function, right? It's called a motion. It's a motion. All right. So Kirchhoff assumption basically results in this simplification of the displacement function.
Okay, that's not what that means, but I appreciate that.
So basically, your z direction motion everywhere only depends on the central plane motion. If the mid plane move down a certain distance, every other plane of this you draw a vertical line, all the point on this line move the same amount in the z direction. This is what the equation says. This equation says the z direction motion is basically determined by the mid plane motion in z direction. Okay. And the top equation says the x direction motion is the center line movement plus the effect due to the pivoting. This is the effect due to pivoting, because your normal pivot a little bit, and the further away from mid plane, the more it goes that direction. It's like a slope thing, right? So this is basically this much. And this motion from here to there is this first term.
Just partial.
Okay. So it basically says the x direction motion is due to midplane motion plus the pivoting of the normal. And same thing here. Y direction motion, V function, is the midplane motion plus the pivoting of the normal. This is the pivoting of the normal. Okay. All right. This is the result of a Kirchhoff hypothesis. This guarantee, this is in line with the assumption, geometric assumption we made early on. The normal remains normal before operation. That whole set of equation is this. Okay. Now, what's good about this is that it greatly simplifies your strain. We can calculate the strain using displacement. How do we calculate strain from displacement? You do the partial derivative, right? What's the EX? What's the epsilon x direction? If you know motion, it's a partial u partial x. Remember? What's a gamma xy? Yeah, what's a shear strain? How do you go from displacement to shear strain? It's partial u partial y plus partial v partial x, right? So you can do the partial derivative of this function, give you the strain distribution, right? So you can basically apply, this is you can calculate this, but doing the partial derivatives. If you use those equations we learned before, you calculate this strain. This is in-plane strain. Basically stretching x, stretching y, and a shear in plane. You plug these functions into the strain calculation function, you get this.
It will be paid with a credit card.
All right. So this is the beauty of the Kirchhoff hypothesis. It basically tells you the strain anywhere in the plate is pretty much determined by the strain in the midplane plus a bunch of curvatures. So if the midplane has a curvature in xy and xy, this is a twist basically. This is a curvature and curvature y. This is the twist rate. It's also a curvature. The twist rate is by definition is equal to this.
I have a question. If the car gets here and let's say some of your
the strain anywhere in the plate is the midplane strain plus the curvature multiplied by z. Z is the distance from that plane to the midplane.
Get a potential refund of that transfer fee,
okay,
since it's not the car that I'm ordering?
This actually results in great simplification when you later on do the calculation. So it basically it almost reduced the dimensionality of the problem. It's a 3D problem. You reduce to almost a 2D problem plus the distance. You can just follow the midplane. Basically, the midplane, how the midplane move and distort, basically tell you how other material below the midplane would behave. This is what it means. So midplane strain plus curvature multiply a distance.
Yes.
Okay.
Everything's okay.
So what's the unit of curvature? What will be the units of curvature?
No other questions.
What's the unit of the strain? Partial u, partial x. No units. What's the units of this curvature? The curvature of units? Now, if I draw a circle here, what's the curvature of this circle? Curvature is, what's the radius curvature? It's 1 over the radius curvature, right? It's 1 over the radius. Can you describe radius without dimension? You can. So curvature has units. curvature is as units. Okay, it's 1/meter. And you multiply meter, that becomes unitless. This is 1/meter, multiply meter. Okay. So if I draw a circle here, the radius, 1/that radius, the curvature of the circle. The smaller the radius, the more curved it is. 1/r. Smaller the r, the bigger the radius, the bigger the curvature. If r equal to infinity, curvature is 0. That's flat, right? Okay. Okay. This is the direct consequence. We talk about the consequence of Kirchhoff assumption. This is a direct consequence. This is a second consequence. This is all geometry. Okay. All right. So so basically, you can think if you think about the strain dependence on z. The strain dependent on z. You look at the strain. You do a perpendicular line through the plates. You look at the strain. The strain is actually proportional to z, right? The z dependence is this term. These are all constant. At certain location of the plate, the curvature is all constant, right? Curvature is this. Let's say you know how the midplane would deform. You know this midplane deformation. The curvature will be fixed by that midplane deformation. This will also be fixed, and then other strain will really is function of z. So you think about if this is a plate thickness, the strain must be the linear function of that thickness along the perpendicular lines through the material. Okay. All right. So if the material is not homogeneous, different layer, different modulus. If your strain is a linear function. Now, assuming the moduli of the material varies from layer to layer, and the stresses actually is discontinuous. Stress is this multiplied this, right? That's a continuous function. Strain is continuous function. Moduli is discontinuous. Different layer have different stiffness, along this direction. And then you can imagine the stress will be like this, right? Is this factor multiply this? So this gets scaled. This string gets scaled by this modulus. So it could be like this, right? So the stress is discontinuous. Or you call it piecewise continuous. There's a jumping condition along the interface. The stress jumps from one layer to the other. Okay. The strain is continuous. Stress jumps. Okay. All right. Let's get resultant force. This is a measure of loading. If you cut a material element out of a plate, you look at all the forces, all the stresses in each layer. Let's say you look at all the forces in each layer going through x direction, point to x direction. Every layer would have a stress sigma x. It could be different. We know the stress has jumping situation. Stress varies. And then if you sum all the stress up in x direction up, you sum every layer, sum the x direct stress and up. Obviously you multiply the dz. Dz is how deep each layer is. And then since they have the same in-plane dimension, so this actually is a measure of the area. So, and then you end up having this quantity is the sum of all the stress in x direction, which give you a measure of loading condition along x direction. We call this thing resultant force. Okay. Is the total effect due to the stresses in x direction of all layers. This is a total effect. Now, since you have more than one stress, you have a total effect because there are shear stress. You have a total effect in this direction as well, on this section. So you call that nxy. This is calculate this by this equation right here. And then you have ny. Okay. All right. Why do we need this? We need this so this this total effect, actually, if you have a load applied this direction, this total effect was balanced load. For equilibrium, usually that requires your resultant force matches whatever your applied load is. This is what satisfies the equilibrium. Equilibrium is the sum of all the forces in certain directions, matches whatever your external applied effect. So this is the sum of those things. You later on use this to satisfy the boundary conditions, with external loading. Okay. Now let's figure out what will be the unit of nx and y. If you look at the equation, what will be the units of nx and y? Now you know the unit of sigma x, do you? What is the unit of sigma x? That's a stress. Pascals is force per area. Now, what do you say the nx? What do you say? Is nx force? Pascals or what? Why? Can you explain? It's a force per area become force per length. So the way I understand is what's the unit for dz? Yeah. So you multiply them together. You have a stress multiply a length. That will become force per length, because stress is force per area, right? Force per length by mass length. And then you integrate to sum. Sum doesn't change units. You just add small pieces together, right? So that will be the force per length. Now, if you tell the size of this plate in this dimension, you can calculate the total force. You just take this number, multiply the total length in this direction. That will be your force. So this is not a force. This actually is a linear density of force. You can think of it that way. What this actually really is force per length in this direction. But this one is force per length in this direction. Okay. So you can calculate the total force. Total force will be this linear density force multiply how long this is. This force will be this linear density multiply how long this is. Why the z dependence drops out? Right? Imagine force is stress time area. Why? That's already taken care of. That part is taken care of through this integration. The z dependence already taken care of. So it's like a calculate force, but you just integrate it. When you calculate force, you need to integrate across the area, z and x. But this calculation does integrate z, ignore the x. So that results in the x density, but z dependence already taken care of. Okay, so this is a weird quantity called the resultant force. When you talk about plate theory, a lot of people use this to describe the loading condition of a plate. It's a linear density of a load. It's not a pure load. Okay. All right. So there are also moments, just like your beam theory. Your beam theory has internal moments. You cut a beam in cross section, there are moments. They're like bending moments. For plate, there are bending moments as well. They're not only bending moment, there's a twist. There's a twist. Twist is analogous to torque in the shaft. So if you cut any section out, there's a moment, there's a twist. Okay. And you can also calculate the moment. The moment is calculated this way. Okay. So you basically you calculate a moment by a little force multiply a distance z. This z term is what makes a moment. Now this force density without a z, see here. This one has a z here. That actually gave you the moment. You can calculate two moment, mx, my, and mxy. Again, there's a linear density because we didn't integrate with respect to y in this case. So this all per unit length. Okay, so let's say you know mx for this plate. You know this length is 1 foot. You multiply mx with 1 foot. That will be the pure moment, total moment over that section. Okay. And the unit mx will be the moment per unit length. This is moment per unit length. This is also moment per unit length. Okay. So moment per unit length, it turns out as units of force, but that's really moment. That's what's weird. You get confused. But the true unit of mx in this is Newton or pound. But what it represent is the moment over length. Okay, over certain length. All right. Any questions? All right. So this is a shorthand for you. You can express this in vector form. You can put this 3 equation in vector form. You can define a vector of forces. It's just another way to write this 3 equations together. This is a oops, back. All right. Here we can introduce our constitutive properties, because we know the sigma x, sigma y, tau xy really depends on strains. Stress and strain are linearly dependent, right? If you know the strain, you multiply strain with a matrix, you get stress, right? So the total resultant force, as we said, is the sum of stress along the sigma direction in certain ways. And so that becomes this. This integration can be break down into layers. So the other way to say it, when you integrate, this is a better one. When you integrate from minus h/2 to plus h/2, you can integrate from z0 to z1, and then integrate z1 to z2. This integration can be broken down into integration over each layers, and you sum those integration together. You integrate from z0 to z1, you sum another integration from z1 to z2, right? It's the same thing. You just break into different intervals. And that's what this is. This is a total integration from top to bottom of the plate. This is a break that integral into different intervals. Each interval represents a layer. If there are total n layers, you integrate from 1 to n layer. And this is each layer, you sum them together, right? So nothing changed except that you basically evaluate this integral into n intervals, okay? You sum them together. And then we can further substitute sigma x, sigma y, tau xy with strains. We know there's a relationship between them. There's a linear relationship between them. You can substitute all these stress terms with this terms. And then okay, and then we know the strain is 2 effect together. Strain is the mid-plane strain plus a curvature effect. It's a linear dependent on z. So we change the strain into this form, which give you this. So this strain is a 2-term sum together. One is the mid-plane strain, the other is the twisting effect due to Kirchhoff absorption, right? So this single term now break out in 2 terms. Now remember, there's a z terms here. This z came from this z here. Okay. All right. So the stress in each layer can be expressed into this form. 2 terms. One is a mid-plane strain multiplied by matrix. This is a z multiplied curvature multiplied matrix. This is the same matrix, by the way. This matrix is same as this matrix. Is this a matrix? This is a matrix that you transform into from the material coordinates. You have material coordinate matrix, you transform into global coordinate, that's the matrix here, okay? We call this as a stiffness matrix, Q, okay? S is a compliance matrix. All right, now we can stick this sigma term in this form into this equation here. And that becomes this. It's kind of messy, but if you look at back and forth a few times, you get it. So basically it's a midterm strain multiply a matrix. You integrate over each layer and sum them up. This is a curvature, multiply this matrix. And then there's a z term, the z in the back. Z is blocked, I think. There should be a z. Z there, okay? There's a z here. And then you integrate and you sum together over the layers. So this is the equation. What do you call this equation? This is equilibrium equation. This is just equilibrium, okay? Basically, it says external load matches the internal stress. Internal stress is balanced with external load. This is what it is, okay? All right. So further simplification, I think this is the same equation. We just change the integration. This whole thing can be taken out of the integral. Why? You see, from here to here, look at the difference in the first term. This and what's this? What's the difference? Now, what's the difference is this whole thing is taken out of the integral. See, this is taken out. Oops. So what happened? Why? Do they depend on z? Is epsilon 0, gamma 0 depend on z? No, it's not. It's a mid-plane strain. The mid-plane strain is a strain of a particular plane. It has no z dependence. And Q also has no z dependence. So you can take them out. Okay. So basically, you can, because this thing, z, you can take them out. Same thing with the curvature. Curvature doesn't depend on z either. Okay. So this integral with z term really can be evaluated separately because that really doesn't depend on z. It's a constant, right? This is a constant. And that's a constant. They can be taken out. Okay. So you can basically evaluate this integration alone, multiply this, and same thing here. You evaluate this integral alone, multiply this. And this turns out to be the thickness of each layer. It's integral of 1. Integrate 1 dz from hk minus 1 to hk is just the thickness of that layer. Now, what's this term? Is that thickness too? That's not thickness. It is a unit of area. It's equivalent to, sort of analogous to a secondary moment, I term, things like that. So this actually is not a thickness, but similar. It's similar to be a cross-section property. is has units of a meter squared. Okay. So, and then you can define these terms. That's the thickness. This is this term. And the overall calculation become this. You absorbed the z terms, integrate z term with a q. You put this two together. This integrate z term, this and q together, that become a matrix, and this together become a matrix. You call this A and you call this B. Sorry. So A is just another name for the integration of Z multiplied Q. Q is a layer property. You sum over all the layers. This is a Q, you sum all the layers, and this is the thickness location of layers in Z direction. You call this matrix B. Okay. All right. And then you have the relationship that describes the external load as a function of a midplane strain and the midplane curvature. So everything now boils down to midplane dependence. There are no dependence on other than midplane. Okay. You see the direction we're moving is we're trying to reduce dimensionality of the problem. We try to condense all the calculation to the midplane. Then we solve the midplane strain and midplane curvature. It's a similar problem, like a 2D problem. 3D become 2D. Then when you figure out the midplane strain and curvature, you can calculate strain and curvature everywhere. You can go back. Once you calculate the midplane strain and curvature, you can go back. You can calculate strain, right? The strain, if you know the midplane strain and midplane curvature, you can calculate strain everywhere, right? This is the strain over the whole body. If you know the strain over the whole body, you can calculate stress anywhere, which is this equation. The stress anywhere can be calculated with this, right? So we did a whole bunch of this kind of we're running circles. But long story short, we basically transformed the equilibrium equation that only depend on the midplane strain and midplane curvature. Okay. All right, so this is whoops. All right, so you can this base says that you can back calculate. Once you figure out, if you know the midplane property, you can calculate stress and strain everywhere. Okay. The result moment. This is we only talk about the force, but this is a force balance. Then we can also talk about the moment balance. The moment balance is the external moment matches the total internal effect. This is the moment balance. You can do a very similar exercise. You basically plug in the stiffness matrix into this. You plug in, and you evaluate integration, and you also take the midplane quantity out because they don't depend on Z. You take them out, and you call the remaining part matrix B and D. This matrix, why this becomes Z squared? Anybody follow this? Why this becomes Z squared? What happened? Where does Z squared come from? There's one Z here. There's a Z squared here. Now let's just. So what happened is we plug this into it. We plug sigma equals this into it. There's a Z here. You multiply Z over here, and then Z multiplies this, and Z multiplies Z here. That's Z squared. Okay. Make sure you didn't fall asleep. That's how there's Z squared over here. So it's not error. There's Z squared. because when you substitute the sigma matrix, there's a z term in there, so the multiply z is another z. Why do we multiply z over here in the first place? Why do we multiply z in the first place here? That's because we're talking about moment. The moment is, we talk about resultant moment. The resultant moment is little force times little distance. Little force times little distance, that's total moment. All right, that's what makes a little moment is this z. All right, so when you multiply the second z, it becomes this. It turns out this matrix, if you look at this matrix, for the moment equilibrium equation, actually it's the same as the second matrix in the force equilibrium. You can prove this matrix, the second matrix in the force equilibrium is the same as the first matrix in the moment equilibrium. That's the same matrix. So moment balance become B times mid-plane strain. D is the new. This is the matrix that involves integration of z squares. We call that new matrix. We call that D. All right. Long story short, we just defined the three massive matrix A, B, and D. There are physical meanings. We'll talk about that later. But you can write out this. You can put them in the same block. You basically you can apply the same rules for matrix multiplication. Basically, the dependence of external load to the mid-plane strain and mid-plane curvature can be captured by this 6x6 matrix. It actually is three 3x3 matrix built together. It's a matrix A, matrix B, and matrix D. This is matrix A, this is matrix B, and this is matrix D. So this part is exactly the same as this part. This is the same matrix here. This one is this one. This is a B matrix. All right. So I'll jump ahead a little bit. So the way you solve a laminate is you first figure out what your external load is. And then you figure out these quantities. These has to do with your fiber architecture, mean your layer structure, orientation, material properties. Things factor into this. And you can solve this to get the mid-plane strain and mid-plane curvature. So you solve this equation, knowing this, you solve this. Once you solve this, you know the stress strain everywhere. Remember the strain and stress are dependent on mid-plane strain, mid-plane curvature, based on as a result of a Kirchhoff assumption. So if you're math genius, you can figure out the rest of it. This is basically the whole series. The whole series is this. We're gonna do some exercise. So you end up, you need to solve equations. The classical laminate code, you need to calculate this matrix. That's the majority of the work. You write a code to calculate all these matrices. Given your laminate structure, you can calculate these. And then you solve this linear equations, and you obtain this vector. Then you plug this vector in back into your relationships. You can calculate the stress every layer, strain every layer. And then you can make a decision. At this external load, is this stress at this layer over its limits or not? You can make design decisions. Okay, so this is we've gone through a whole lot of, I'll stop here, we're gonna continue, but this is a little messy. I'll upload the slide to the Blackboard, you can study later. It takes a while to get used to them. Okay, I'll stop here today. I'll see you guys later.